science, and there are scientists who are frauds, scientists who are liars, scientists who are scamming
Don't say that.
And now you're accusing me of logical fallacies for not producing any fucking evidence. Fuck you. So how about, you pony up? Where's your evidence? Where's your data? And don't give me this shit about constructing a horizontal line. Talk to an engineer. The guys who get paid more than you do because they know more.
I got your numbers right here.
Hey Tony, the Earth is flat.
It's just as easy as 1, 2, 3. You have to open your mind.
Hey Tony, the Earth is flat.
Imagination is all you need. Don't take advice from fools. Everything that they say is in vain.
Basically lying, right? Come on.
Never take advice from fools.
We all know you're lying.
We don't know what they do is in vain.
It turns out that your straight line stuff doesn't give the right result. So we give away the straight line stuff and we say maybe there's another geometry.
You think the straight lines?
Yes, we say, well, obviously this distance doesn't correspond to a straight line distance, but it does agree very well with the spherical.
Everything is relative to you. You just have to say it in generalities, just like those straight lines are curving. Drive down the road, don't you ever swerve. And I don't know.
Straight lines can be described as curves.
All of this goes.
We use the Hemisphere formula
Never take advice from
all the fucking time.
everything that they say is in vain.
It's a crap experiment.
Never take advice from fools. Everything that they do is in vain.
Why are you wasting your time if we are the losers?
Because it makes me feel good to make you guys aware that you're losers. And that model, pretty accurate. Spherical model. One-dimensional spherical model.
I know the game that you play.
Hey Tony, the Earth is flat.
And I know exactly what's on your mind.
You're a specialist in flat Earth models.
You got your playbook, it's alright.
Core drill.
Your model
Core drill.
will find.
Hey Tony, the Earth is flat.
I don't know.
Core drill.
All of this
Core drill.
This is a crap experiment.
Don't take advice from fools. 'Cause everything that they say is in vain.
Hey Tony, the Earth is flat.
Never take advice from fools. We all know what they do is in vain.
Hey Tony, the Earth is flat. If you have a gravimeter below the water, actually gravity is slightly less because the water pulls upward on the gravimeter. So again, yes, I'm a dick. I'm an arrogant dick, right? I know I'm an arrogant dick. Calling me an arrogant dick doesn't change the fact that I'm right. Right?
Come on. Seriously.
A straight line can be described as curved.
I would absolutely not say that straight lines are curved, because in that case the term straight loses any and all meaning. A planar triangle is a subclass of the more general
Don't
triangle.
take advice from fools. 'Cause everything that they say is in vain. Never take advice from fools. We all know what they do is in vain.
But also, I'd like to return to solid earth science for a moment.
Honey, listen, I know you're an arrogant dick, and you know how I know you're an arrogant dick? Because you act exactly like I do, and I'm an arrogant dick.
There you go.
I mean, have you ever wondered why it is that the globe Earth side is full of people who just want to yell at you?
Angular distance. Are these angles with straight lines?
No, they're not. So
You model flat Earth models, right?
I have done, but at the moment, what I do is
Were they accurate?
They were accurate as to the. They were ultimately accurate, yes.
Never take advice from fools. 'Cause everything that they say is in vain.
Hey Tony, the Earth is flat.
Never take advice from fools. 'Cause everything that they do is in vain.
Again, I'm an arrogant dick, and I can only say sorry.
Voice is higher
You
than mine
can't-
at the moment, darling.
You don't. Please don't call me that. It really does disgust me. My PhD thesis was about modelling seismic energy transfer on a flat Earth.
You could have called me JG Chihuahua. That would have been okay.
But my standards are not necessarily in accord with reality. This is a crap experiment.
Yeah, not a level that's useless for surveying.
You know, basically an infinitely dimensional polygon.
Infinigon.
Spherical. Yeah, an infinigon.
Take advice from fools. 'Cause everything that they say is in vain. Never take advice from fools. We all know what they do is in vain.
Okay. Yes, all maps are flat. That's the definition. Well done, you.
Because you can't explain it.
Yes, I can. I'm not going to because you're a dick.
Oh, thanks.
You're welcome. And I've determined that all of you are just dicks.
Wow,
You
Tony.
find help.
That
That's
was awesome.
Great.
Makes you feel good.
Yeah.
And thank you very much. It's a valuable public service you provide. I mean, have you ever wondered why it is that the globe Earth side is full of people who just want to yell at you? Right? I'm here and I've tried to
Are
present
they all like you?
observation. No. Most of them are vastly less well educated and most of them are vastly more stupid than I am.
Wow.
Yep.
Yeah. That's what
Most-
PhD does for you.
Most Globers are
Yeah.
dumb. I mean,
Yep.
oh,
That's true. I mean, you know, deny it if you can.
I'll agree with that.
Yeah, they don't have a
But-
they live in their mom's basement.
But the vast majority of them are vastly more informed and vastly more intelligent than you guys. And the thing about, you know, that there are a couple of exceptions. But the vast majority of you have no interest in learning any information whatsoever, right? And which is just like the globe earthers. A lot of globe earthers aren't interested in learning stuff, aren't interested in acquiring new intellectual material. They just want to yell at you guys and feel good doing it because nobody tells them off. That's the
And how
dynamic.
does that make you feel?
What about them yelling at you? They can do
Jealous.
whatever they want.
I bet you're jealous, aren't you? But you wanted to be there yelling at them.
Not really, no. You know,
It make you feel
if I
good
would,
though.
if I would, no, not really. I mean, it's good to have this sort of experience to remind myself why, for instance, I don't have debates on my channel, right? Because I keep on thinking, you know, surely if they get information that they didn't have before the start of the discussion, they'll process the information. They'll look at the information and they'll assess the information, right? Surely that will happen for at least one of these people, right? They don't know about gravimetric mineral surveying. They don't know about gravity gradiometry. They don't know about mapping the ocean floor. They don't know about satellite gravity missions.
You don't know
Right?
about it, Buster. He's right.
Oh, come on. I worked in mining for years, and they just went out and core drilled. Core drill.
Okay.
Core drill.
Google.
Core drill.
Google.
Core drill.
Google. Gravity gradiometry.
Core drill.
Okay, how many professional seismologists did you meet during this
Core
experience?
drill.
How many professional seismologists did you meet?
I just core drilled till they found how far the seam went.
Were they amateur ones or professionals?
So what did you
No.
So what was your role in these mining? You know, were you in the room with the geophysicists when they were saying where to drill the cores?
Wasn't geophysicists. They went out and core drilled.
So you didn't even bother to look up the term gravity gradiometry.
I was actually like 800,000-900,000 foot underground.
You didn't look up gravimetric mineral surveying.
They didn't need to. They went out and core drilled to see where the seam ended. They just drilled.
Who told you where to do it? Well, yes, but that's after you found a seam, right?
Fantasy.
In that found a seam. That is after you already know where there is a seam, right?
They just drilled. They would drill.
Okay, so yes, they would drill.
Yeah,
and somebody would tell them the best place to drill.
No.
And that person, yes, somebody who earned more than you did told them to drill here.
Okay.
Yeah. Obviously, how can you come back from that?
No, I can't.
I really hope that you don't talk to your children like this, and I apologize for whatever your father did to you.
I don't have children.
Thank God.
Obviously.
I apologize for whatever your father put you through.
Quite frankly, I don't think I'd make a good parent. But you know,
I agree.
That aside, and I hope that you guys don't have children that you're brainwashing. So again, yes, I'm a dick.
Ooh.
I'm an arrogant dick, right? I know I'm an arrogant dick. Calling me an arrogant dick doesn't change the fact that I'm right? It doesn't change the fact.
He did say right afterwards that.
Calling me an arrogant. Let me repeat that. Calling me an arrogant dick does not change the fact that I am right.
We didn't call you that. You did it yourself.
Yeah.
I know.
You said you were.
Yes. But, you know, implying that I'm, you know, character observations, well, you're just an arrogant dick. Yeah, I know I'm an arrogant dick.
You've just said it.
Well, yes.
You can't call yourself an arrogant dick and then say, just because you call me an arrogant dick doesn't mean I'm not right, because I am right. Because I called myself an arrogant dick.
Who in this conversation doesn't think I'm an arrogant dick?
Who doesn't in this conversation think
that I'm an arrogant dick?
Does it mean that you're right if we say that you're an arrogant dick?
No, it's irrelevant. It's irrelevant, right?
Don't pinrose yourself.
I mean, that's the point.
Okay then,
right?
Tony, you are right. You are an arrogant dick. I will agree with you on that.
Yeah, okay.
Tony, listen, I know you're an arrogant dick, and you know how I know you're an arrogant dick? Because you act exactly like I do, and I'm an arrogant dick.
There you go. Look at that.
Okay.
Come out in solidarity.
But you know, it doesn't change the facts, right? I mean, I can be, you know, like there are, you know, you talk about science, and there are scientists who are frauds, scientists who are liars, scientists who are scamming people.
Don't say that.
Well, it's true. It's a reality. I mean, the field that I work in, there's a guy who is
not the science I've heard about.
Well, I mean, I'm talking about scientists, the people who, you know, are paid to do science. Scientists are humans, right? They're not. You know, yes,
That's not what
they're
I've
well
heard.
educated, and they're
Science. Be careful. You're attacking the whole body of science. You can't be doing that.
No, I'm not. I'm trying to make a point here. The existence of individual scientists who are, you know, bad actors or who are acting in bad faith doesn't change the general constructive nature of science. And this is something that I think, you can admit when a scientist screws up. A scientist can even get a fake, like a bad answer, a bad experiment, and still claim that they got the Milliken oil drop experiment is the example that I'm thinking of, which is an experiment about how quickly oil drops move up. You spray oil drops into an electric field and they acquire a static charge, and they move upward against gravity at a particular rate. And from the rate the oil drops go up, you're supposed to be able to work out that electrons have a distinct unit of charge. That's the basic principle of the experiment. But it's a crap experiment. When you look at it, if you go into the apparatus, you're looking down this sort of binocular set. It looks kind of like a microscope. And there are these glowing dots that are fucking going everywhere, and you're supposed to be measuring how quickly they're going across the dashed lines. It's impossible to keep track of them, and you're supposed to be timing them. They're going so bloody quickly. This is a crap experiment. I don't see how anybody got a result out of this.
What about the Schehalian one that you've just been talking about?
Am I off?
Except that okay, you can look at an experiment. Okay, an experiment can give a result. Now you go out and you validate it, right? You try and validate it, or you try and challenge it. You go and you see, if I do this a different way, and avoid the errors in that formulation. And you're right. You know what? There could be errors involved in the positions of the stars. There could be errors in the way they've set it up. They may not have correctly accounted for wind. There may have been some other factor involved. So you go away and you validate it. You do it a different way, right? You do a similar experiment that's going to get a similar value, but you do it with a different methodology. And that's what's been done many, many times. And that's why I emphasize, yes, with the Schehalian. The basic form of that experiment has been validated many, many times using different methodologies. They haven't done exactly the same thing. They haven't deflected, they haven't gone out and measured a mountain that often, but they have determined that mass attracts mass according to Newton's law and the approximate value of the gravitational constant in multiple different ways. I mean, I was looking at a. We just have
to what stuff we can do.
I was looking. Well, no, I fail to see why what you can do is in any way relevant to science, right? I mean,
you say we can't do science? Should be acceptable and available to all, shouldn't it?
No, absolutely not. I mean, for starters, okay, do you think you in your home right now, do you think you have the equipment to put together your computer? No.
I've got a computer.
It's specialized equipment.
Can I just ask? Can I just ask, what did you get your PhD in?
Geophysics.
There you go.
The physics of the Earth.
Earth physics.
The discipline you think doesn't exist. In particular, I developed techniques for modeling the deformation of. Yes, a flat Earth model for deformation of the Earth under surface loads, for instance, under large ice sheets, and the change in gravity that results. One of our big indicators is paleo sea level, and in order to get paleo sea,
the flat Earthers thank you for it. Your tireless work.
Well, it turns out that it was almost completely useless, and we've abandoned flat Earth models for what we're doing. But thanks for the good wishes.
No, not for me. I bet the flat Earthers. You never tell them that you tried to do it for them.
No, I tell them all the time. Because
so when everybody says,
up,
"Where are the flat Earth models?" you say, "PhD, Tony's got them."
Yeah, so I mean, I worked on a flat Earth seismic model and adjusting it from size. It turns out that you can adjust sort of the seismic formulation to the problem I was considering, which was viscoelastic, with a little bit of mathematical sorting out. But and it comes up. We use them, as you guys were saying all the time. We use them all the time. We use flat Earth models all the time because over short distances, it's a good approximation. It's a great approximation. And your mining friend. So all of the seismological models that is used for mineral exploration, flat Earth modeling. Undoubtedly, because the errors involved. The errors involved are small, and sorry for pausing, but it reminds me of something that my PhD supervisor told me that sort of stuck with me. He said, every mathematical model is wrong, right? No mathematical model is absolutely correct. But some mathematical models are useful enough, they're accurate enough that they can be useful. And that's what we aim to achieve. And over short distances, flat Earth seismic models are fine. They're accurate enough. They're really, really good. But over larger distances, they fall apart. You can't make them work. It's just reality. And I know Paige was referencing somebody else's work, but it's just not the case, right? You can look at the Rayleigh wave propagation. Rayleigh waves, radiate outwards in a circle, and they come around. They do it multiple times, and the way they progress through, it's just perfectly circular. The only way it can be circular for every earthquake and every seismic station. And in fact, for every earthquake, we can do tens of thousands of predictions, and we get them pretty much right. Right. Once we know where an earthquake is, we can predict for every seismic station on the planet when the various phases of seismic energy should arrive at that station. And we've got a model that tells us when that ought to occur. And that model, pretty accurate, spherical model, one-dimensional spherical model. We assume radial symmetry. We assume that the S and P wave velocities don't change as a function of latitude for that purpose. There are more sophisticated models that do assume that, and they also assume various other complexities. But as a first guess, it's a pretty good instrument. And if the Earth weren't spheroidal, it would not be possible. It would not work.
What is S?
And if you, a P wave is a pressure wave, and that is sort of a compressional wave. So if, I can't. So a P wave basically, imagine an explosion that pushes the material next to the explosion out, and that material then rebounds, but it's pushed the material next to it out, and so that's it's a push wave. It pushes.
So you don't. So you think these can't happen on a? Okay.
No. This is the point. They can happen on a flat Earth, and we do use flat Earth models to model these processes. But it's the travel times that are the problem, right? When you've got a global network of stations, would you mind if I? Can I share my screen on this? Would you mind if I shared my screen and tried to show you something?
Yeah, we're here to learn, man. We don't care. We just want to. If it's something better than at-homes, and whatever.
Yeah, I tend to resort to ad-homs if I think that it's being an intellectually dishonest conversation, but my standards are not necessarily in accord with reality. People can sincerely ask me questions that sort of trigger an overreaction on my part, and I apologize. But again, I'm an arrogant dick, and I can only say sorry.
Fair enough.
Okay.
Well, P wave is a pressure wave. What's an S wave?
So an S wave is just shear wave.
Shear?
So shear wave, yes. So if you imagine a rope next to you and you wave it side to side, that's a shear wave. Okay. So it's a wave in which the deformation is orthogonal to the propagation of the wave.
That's just 90 degrees.
Yeah. That's right. Yeah, that's a
Okay.
shear wave. Yep. Those are the so shear waves don't go through liquids. It's important to realize that. Okay, a P wave, a pressure wave, will go through any compressible medium. So it'll go through air, it'll go through water, it'll go through any liquid or fluid or gas. Fluids actually refer to liquids or gases, but it'll go through any fluid. A shear wave won't. Okay, because a shear wave relies on the material being able to resist shear forces, and the defining feature of fluids, liquids and gases, is that they don't retain their shape. They don't resist any shear forces whatsoever. If you wave your hand backwards and forwards, you're going to propagate sort of at 90 degrees. You're going to propagate a disturbance at 90 degrees to that. Anyway, so those are the two basic classes of wave, but when they interact at a free surface, they create what's called surface waves, and there are two broad classes of surface waves, Rayleigh waves and Love waves. They're both named after people.
There's L waves?
Yeah, there's, I think that maybe the notation is L waves. Again, I'm not, this is not actually my speciality. My speciality is a little bit different, but yeah.
But a P wave is pressure, an S wave is the shear wave.
Yep. And if you're looking it up, there ought to be surface waves are the two classes. There'll be Rayleigh waves, Rayleigh, like Walter Raleigh, and there'll be, or Rayleigh, if you want to, I guess I should use Rayleigh since you guys are familiar with that pronunciation. Yeah.
I thought the Rayleigh thing was like optics stuff.
Yeah, it is, but he did a lot of more general science, and he discovered this particular type of waves, and they're actually, it's probably because light travels in waves, there's a lot of sort of crossover, and back at the time, sort of seismology wasn't its own discipline.
So there's a crossover between the way light travels and the way,
in the sense that that under some circumstances light can exhibit wave-like properties, and certainly in seismology we're looking at the transmission of waves. You've also got the same idea in terms of interference patterns and Huygens principle and that sort of stuff. We're looking, so the general mechanics of waves is something. But yeah, so the Rayleigh waves are a form of seismic wave. They come from the interaction of P waves and S waves as they approach the surface. And so they're only formed for actually some earthquakes. Only you need an earthquake source that is actually close enough to the surface to generate Rayleigh waves. If it's too deep, it won't generate Rayleigh waves because the P waves and the S waves have different velocities and they won't arrive at the surface close enough to interact. The P waves will get there much faster and be gone, and the S waves will turn up too late for Rayleigh waves to be generated. Anyway, so sorry, I'm just looking for the graphics that I put together on this. Okay. So getting back to you guys.
I think that's
Can I do that, or
why the USGS folks thought what I saw probably the surface waves, because that was a fairly shallow earthquake.
Yeah, and so the sorry, I need to just add Discord.
Shallow earthquake, but it was fairly far away.
Yeah. Well, that's the thing. Like the rally waves remain coherent for a long time. If it's a big enough earthquake, they'll travel a long way. They'll go multiple times around the Earth. So okay. Just a second. I'll be right back.
Yeah.
Well, 7.2 is a pretty big earthquake.
It is a pretty big earthquake. Okay, so let's see if this will work. Okay.
How far away was Haiti from wherever the Cavendish was?
2,200 kilometers. Yeah.
200 kilometers?
Okay. Yeah.
2,200.
2,200. Okay.
Yeah, so maybe about 1,400 miles.
Yeah,
If that
something
makes
like
it
that.
more achievable. Okay, so if you look at my screen, which I'm sharing, you'll see sort of the pressure wave, pushes stuff close together, compressing it, and then it'll expand. But in expanding, it compresses the stuff that's next to it, and so it's a push wave. It's a pressure wave that is pushing the material next to it, and the shear wave. Yeah, well, a push wave is not official notation, but it's that's sort of how it's working.
Pressure wave.
It's a pressure wave, yes, or a
Okay.
compressional wave. Yeah, and the S wave is down the bottom there, and that's a side-to-side motion. So the wave is going to the right, but the material is shaking up and down, sort of at 90 degrees to where the wave is going. So this is more our traditional view of what a wave looks like, right?
Whoa. Okay, so wait a minute. You're showing them both in linear functions, but you're defining them in.
Yeah. This is just a schematic. Okay.
Yeah.
This is just a schematic illustration, so that we know the styles of waves that we're talking about. Okay.
Well, but it's not that helpful though if you're gonna describe them in different. Okay, let's see.
Okay. So this is an example of a rally wave, which is sort of an accordion. Like you get compression at the top and expansion at the bottom, then you get compression at the bottom and expansion at the top, and it sort of goes like that. And they're actually the most destructive of the seismic waves. So these waves are.
Because they hit faster.
No, because they result in more up and down movement of the surface. So there's more vertical motion, and it's vertical motion that's really damaging during an earthquake.
So like if the diagram you're showing on the bottom with Rayleigh waves, is that showing that verticals move with reference to?
No. So if you look at those red arrows that are sort of drawing an ellipse, sort of an egg shape down the bottom, the local material, that's what the local material is doing. It's basically moving in a little ellipse there. But the wave itself is traveling beyond that. It's like in a water wave, we tend to think of the water as moving. Mostly it doesn't, right? It's the disturbance of the water that's moving. But the water particles themselves tend not to move much. So that's why, and the physics of waves are actually a bit complicated when you get down into it. But up above that schematic is an example from the Sumatra earthquake of 2004. and it shows, R1 is the rally wave that came straight from the earthquake towards Marble Bar, which is in Western Australia. R2 is the wave that came the other way around the Earth. R3 is that first wave coming back around, and R4 is that other wave. The red ones are the waves that propagated away from Marble Bar, came around the back of the Earth and did that, and came up behind it. And those blue ones are the rally waves that came direct from the earthquake straight to Marble Bar, then went round and did another lap and came back again. And I mean, we can tell the direction that earthquakes come from because we've got, massive networks of seismic stations. Like this is the
triangulated.
Yeah, so these are all of the triangles here are seismic stations, and if you look at the middle of Australia, I don't know if you can see my mouse. Sorry, there's a red triangle. Yeah,
triangles with 180 degrees.
Yeah. But this is the Warramunga seismic array. So this is one of those little triangles on the surface of the Earth, and you can see that it's actually got 10, 20, 24 seismometers, and they've set up the seismometers so that they will pick up seismic signals at different times so that they can tell what direction the seismic energy is coming from, so they can work out sort of just from the arrivals, even at this one seismic station. And this is just one seismic station, and we've got lots and lots of them around the world. So we look at these, and if we look at the data from these, this is on the left-hand side here. So those dots are the observed arrival times for different seismic wave phases. Okay, and the solid lines are the model fits. The model fits, and on the right hand side is the more complete model. Now, if there's an earthquake, these are surface normalized. So if there's a surface earthquake and we've got a seismic station, all we need to do is calculate the angular distance from the source, the angular distance. So let's say we pick an angular distance of 60 degrees. We go across that bottom, across to the number 60, and then we just go up. And the first wave to arrive should be a P wave.
Angular distance, are these angles with straight lines?
No, they're not. So the angular.
Wait a minute. How can you have an angle without a straight line?
Okay, I explained earlier to you how you can have an angle without straight lines. Would you like me to repeat the explanation?
No. Well, if you have an angle without straight lines, wouldn't your angle change?
Here's how we calculate the angular distance between any 2 points on Earth for which we know the latitude and longitude. Now, if you're a flat earther and you want to prove that your model is correct, this is a prediction. You give me the latitude and longitude of any 2 points on Earth's surface. That formula, phi equals arc cos sine whatever. That's the angular distance between them, and the distance in kilometers is just the radius times that angular distance, and that should be a good estimate. Now, if you can find any 2 points on Earth's surface where that doesn't do a good job estimating the distance, then you are well on the way to showing that the sphere model is a bunch of crap, right? If you can find any 2 points on Earth's surface for which this doesn't work, right? Any two, just look them up, show me that the distance between them is not well estimated using this technique. I'll
2
believe
points
you.
is well.
Any
The
2 points.
shortest
Any?
distance between 2 points is a straight line.
Yes, provided you're not constrained to travel through across the surface of a sphere.
That sounds like a presupposition.
No, it isn't. You're, and no more than you saying that the Earth is flat is a presupposition.
I didn't say the Earth was flat.
I'm saying we can test. I am suggesting that using this. Okay, so you're saying that the linear distance between 2 points.
Don't say you're saying because you're trying to put me within your framework.
Calculate the distance between any 2 points on Earth's surface and show me that it's different from this.
Different from what?
This formula. I'm showing you a formula here. I don't know what latitudes and longitudes you're going to pick. I don't know. I have no idea what latitudes and longitudes you will pick. But this is the formula that I'm going to use, regardless of the latitudes and longitudes, and I'm going to bet that it's a good estimate to the distance between the 2 points. So pick any 2 points where you know the distance.
Latitude and longitude. I mean, latitude and longitude. Where'd latitude come from?
Okay, latitude comes from the elevation of celestial objects, in particular Polaris, above the horizon.
The elevation
the apparent angular elevation of Polaris above, if you're in the northern hemisphere, the apparent angular elevation of Polaris above the horizon is 90 minus your latitude.
Well, then how do they?
It's just your latitude. Sorry.
Oh yeah. Look, I'm not trying to be smart aleck or nothing, but you said say it again.
Okay, so the latitude is the apparent angular elevation of Polaris above the horizon.
Well, then how do they do southern latitudes?
Okay, they take an object whose latitude relative to Polaris they know, and then they work from that. Okay, so let's say we've got a star that's 45 degrees. From that, now I can work out my latitude relative to that.
45 degrees to Polaris?
From Polaris. 45 degrees separation from Polaris. So it's overhead of a person who's 45 degrees south of Polaris.
Man.
So we can extrapolate that way. Or we can plug the values into GPS and solve for latitude and longitude that way.
Well, no, I want to find the origin of this stuff. Like, cause it's been recently I've learned that the latitudes were derived from Polaris. 1 degree over 69 miles gives you your latitude lines, and then the longitude has to do with the time.
Yeah, so it's the time at which, say, for instance, the sun crosses the horizon. Emerges above the horizon at a particular point in year. But it's easiest when you're dealing with the equinox, because the sun should rise at the same time for every point along that line of equinox. So you've got from the North Pole to the South Pole, every point along that line, along that great circle, should see the sun come into view at the same time. So both of these can be determined externally, right? We can determine them externally using other metrics. You don't need to trust the latitudes and the longitudes you've been given. You can go out and work them out for yourself.
Oh well, that was the thing. I was just yeah.
No, they're good questions. I mean, these are if you don't know how latitude and longitude are determined or described, they're perfectly valid questions. This isn't something to be defensive about or apologetic for. I don't mind. If you.
No. I've never been to south of the equator. I didn't know. I didn't know how they figured southern latitude lines.
Yeah, but so they basically work to something that's intermediate in between, and then they sort of piggyback off that to construct. That's how they did it historically. Nowadays, we've got accurate star maps, but if you reject the star maps, we've still got and it has to be borne in mind that these are all approximate. In fact, Earth doesn't spin on a constant axis of rotation; it wobbles a little bit. Not so much that you'd notice if you weren't really paying attention, but it wobbles a little bit back and forth.
Yeah, hey, fair enough.
Excuse me, didn't they also use the Southern Cross in the Southern Hemisphere to navigate?
They did because the Southern Cross, they observed that the Southern Cross tends to point in a constant, the top and the bottom. So the Southern Cross looks like a kite, and as it moves across the sky, the top and the bottom star tend to point almost south, not quite south, but to a point. I think from my time in the Scouts, you take the top and the bottom star. You extend it out about 6 lengths, and that point that it's pointing to is above south, right? So that's kind of how we were taught to do it as a Cub Scout, and as a Scout. But yeah, you can use the, but that's not really that is useful for navigation. That is useful for identifying where south is, but it's not necessarily useful for determining your latitude. Which is sort of the question I was being asked at the time. So,
yeah, cool. Thanks.
And so you can go out and you can take various measurements and you can work out what your latitude and longitude are. And for any 2 points whose latitude and longitude, you give me those points, latitude and longitude, I'll plug them into this formula, and it's not going to be a perfect estimate of how far they are apart, but it's going to be pretty good. And again, if you can find points where this doesn't hold, so this is a falsifiable claim. I'm making a claim you can prove wrong, right? Any 2 points, this formula ought to work. And if it doesn't, there are 2 possibilities. You've done something wrong, or the Earth is not spheroidal. But if you've done everything right, when we check your working, then you've got a solid argument you can present. And I mean, this is key to navigation, right? I mean, when you're trying to work out how much jet fuel you need, or how much food and water you need for a journey, right? You need to know how far you're going to be traveling. And this is how people have calculated it for hundreds of years, right? And it's accurate. It works. People have screwed up and they have died, but there have been a lot of really spectacular successes. Anyway, that's how. So that formula, that top formula, that ARCOS thing, that's how you get that angular distance that I've circled in red down here, down the bottom. That's how you work that out. So if I know where the earthquake was in terms of latitude and longitude, and I know where the seismic station is in terms of latitude and longitude, then I can calculate the angular distance between them, and now I can make these predictions. I can move up from, say, it's 60 degrees. I can move up and I can say that the P wave will arrive first, followed slightly by the PCP wave, then the PP wave, then the PPP wave. There's a lot of P involved. Then there's the PCS wave. the PPPP wave isn't detected at 60 degrees.
What about the
60 degrees?
What about the S wave?
Okay, the S wave is slower than the P wave, and so if you look, you've got P, PCP, PP, triple P, PCS, and then the S wave. The S wave doesn't come in until, so the P wave arrives about 10 minutes after the earthquake at 60 degrees, and the S wave doesn't arrive until about, 16 minutes, 18 minutes, 18 minutes. So it takes about twice as long.
Well, what did Blues Cavendish detect?
What I think Blues, so the most likely explanation is that he detected this green and yellow triangle here, which is surface waves. So you can see the label up to the top right-hand side. That's surface waves.
Those are orthogonal, right?
Well, those are those weird accordion-like ones. That's this thing here. So you can, so they're the sort of weird ones that don't, they're the ones that move the surface the most. Okay, and this is why we think that this is what Rayleigh, this is what Blue detected.
Is that
because
like along along a horizontal plane?
The schematic here is, yes, but in fact I've got a presentation about Rayleigh waves if you want to see it. But maybe you don't. I don't particularly. But anyway, they spread out in a circular pattern. The Rayleigh waves, we can see them sort of moving out in a circular pattern away from the epicenter. And the other thing is that we've got lots and lots of earthquakes. This is a catalogue of all of the big earthquakes greater than magnitude 6 since 1900 up until 2017, so slightly out of date. But it shows we've got lots and lots of earthquakes, and we've even got earthquakes that are pretty close to Antarctica. So we can see the, so we can, we've got some seismic stations on Antarctica actually. If you look down the bottom there, you can see that we've got a few seismic stations, and there's one that doesn't show up. There's one at the South Pole that's cut off by this map projection. But we've got we've got a lot of seismic events. We've got a lot of seismic stations, and in order to match the observations, we need a spheroidal Earth. You can't do it with a flat Earth. Believe me, I'd be delighted if my theoretical development of the model turned out to be the dominant paradigm, but it isn't. And I knew it wasn't before I started. It's just a useful approximation.
You'd be delighted, but then again, you knew it wouldn't.
Well, yes. I mean, if it turns out, hey Tony, the Earth is flat, and you're a specialist in flat Earth models, step up the front here and lecture everybody. But the Earth isn't flat, and and we've known it isn't flat for ages. I mean, I talk about being an arrogant. I talk about being an arrogant prick, but the reality is that the top seismologists in the world, vastly smarter than I am, vastly better educated, vastly more knowledgeable about this subject, and the idea that I could second guess them, absolutely laughable. And perhaps you can look at that as a sign of indoctrination, but I'm just being realistic. Yes, I'm a lot smarter than the average person. I'm a lot more knowledgeable than the average person. But then again, there are people who would absolutely cream me in terms of intellectual and educational accomplishments.
So that
it's a matter of.
But that then derives you to essentially not question.
No, it doesn't lead me. Well, it doesn't lead me to not question, but so the idea is that we want to understand, and you can question all you want, and this is what frustrates me a little bit about the conversation that we were having earlier. You can question all you want, But when I present you with data, surely that has to count for something, right? Surely that has to, if I give you information that you never came across before, surely you should reassess your worldview in light of this new information. And my experience with a lot of flat earthers is that they don't, right? They just find excuses for discounting the information that I'm trying to give them, for trying to discount the data. And I find that extremely intellectually dishonest. Like,
well, they might. I mean, everybody approaches things in a unique way. I mean, data can be great, but imagine this. Let's say I had a purple, let's say that I said that I had a purple elephant in my room, in my house. I've got a huge purple elephant in my bedroom, but you can't see it. You can't, get anything like that. However, I have all this data. I've got pictures. I have, the weight. I have the size. So how valuable is that data?
So well, that's a good question. Sorry, let somebody else answer.
So all I was going to say was the stuff you gave beforehand, previous to what you've got showing right now, was in a horizontal manner.
I think you kind of. I'm not sure that I would agree with that, but
it was like you gave P waves and S waves in a horizontal manner, and then you agreed to
that. Okay.
Yeah,
okay.
I mean,
so those are ideals. Okay, let me just pull up the. Let me just pull up the other. I've got
small sections.
I've got another present. Yeah, these are just small sections of the Earth where but actually we use this all the time, right? So let me just actually get that back up.
Well, yeah, because it's reality.
Well, we use sound waves all the time, right? These seismic waves are just sound waves. They're basically just sound waves propagating through the Earth. That's all seismic waves are, essentially. And we use them all the time. So when we talk about P waves and S waves and Rayleigh waves, they're not just on the Earth. We see them in every application of seismic imaging. For instance, oh, that wasn't right. God, I managed to screw that up, didn't I?
Yeah, but I mean, the whole thing you're describing ultimately depends on these the way stations and the actual stations, and so it's kind of getting into a geodetic issue where it's these larger blocks of detection centers that are actually picking this up, and how they then link that in together with the WGS-84 and the whole National Geospatial Intelligence Agency, which is who makes the WGS-84. So in terms of how you're claiming that this proves a globe Earth, there's several sets of assumptions that could be deceiving you.
Well, they could be. And if you're going to make that claim, you're going to have to show it, right? You're going to have to process some data and show me how this works on a flat Earth. Somebody on YouTube making a claim that they made a model and it all works perfectly.
But it's not about something working. It's not about something working on a flat Earth. Nobody's claimed that as of yet.
Well, if you want me, I have a model and it works, right? And actually, it's a model on which trillions of dollars of infrastructure.
You just made a claim.
And hundreds of.
You just made a claim.
Yes, I did. I've made several claims during this. See this? That's a claim. I claim that for any earthquake, and any seismic station, if it's a surface earthquake, you need to adjust it slightly if it's a depth. But this is for a surface source. The observed order of arrival of seismic phases is going to accord with this diagram. And then I test my claim against the observations in that diagram to the left, and I see that they match very well. Now you're going to have to come up with observations for which my model doesn't work.
That's just seismic waves. You just
So and what?
you just
Seismic
shifted.
waves. Seismic wave. Seismic waves are sound waves, right? I don't understand your particular piece of
Do
mental
sound
agility.
waves travel in a linear function?
No, they don't. They spread out in a circle. But if you, for instance, apply a sound wave via a speaker to the end of a girder or a ruler, say, they'll propagate along the length of the ruler without any side to side motion.
Look,
Right, that's
any
just
sound wave
one-dimensional wave.
any sound wave I've ever dealt with, you have to stay within a linear function of where the sound's coming from, or you get out of that frequency. You won't hear it.
That doesn't make any sense whatsoever. There are ways of reflecting sound waves. You've got to have heard echoes.
All I'm saying is, like a sound that propagates in a certain function.
Okay, mate. You do the modeling. You prove that it's accurate, and you prove that it disagrees with what I get. Okay, because we've done the modeling. We've shown that it's accurate. Okay, if you want me to abandon my model and adopt your model, then you need to put the work into it.
So S waves are sound waves now?
Yes, they're a form of sound wave.
Okay.
P waves and S waves are sound waves.
Well, Tony, what you were just asking there for other people to build you models, if you really want to know the truth of reality, wouldn't that ultimately be your journey? I mean,
yes.
Yeah.
Yes, and this is what we get when we take that journey. Okay, so what we've done, we've gone on a journey where we searched for what best matches our observations.
Well, this is your journey. Your journey.
Well, it's science's journey, right?
Well, if you're tapping into someone else's authority, that's fair enough. That's your decision to do that. But it's still your journey and what you've come to.
But what I think is irrelevant, right? Okay, so as much as I'm an arrogant dick, what I say is only important where what I say is in agreement with scientific understanding. If I were, a demented racist and went on some anti-New Zealand rant or whatever, those stupid Kiwis, what have you, that would not have any validity just because I'm a scientist, right? That would be a demented rant by an angry old man. When I talk about science and what I think might be true in science, that doesn't have any validity. What I think needs to be demonstrated and needs to get past review by my peers, aggressive review by my peers, and it doesn't need to just make it into a journal. It needs to be accepted in the journal. So it needs to be published, it needs to be referenced, and it needs to not be blown out of the water by some work that comes along later. Once it's gone through that entire process, then we can talk about accepting it.
Right.
This
is how they control it.
Who's they?
I do hear what you're. I mean, I understand that that's the process you're involved in.
Yeah, but who's they?
Depends on. Well, in this case, if we're talking about the peer review system, that's a whole. I mean, depends on what in particular, but what you just described as how rigorous it is and how to have that be quote unquote accepted is a foundational and fundamental way that they can control the stream of information. They also use other things such as financing. They use money. There's a lot of different things they use.
Who is they? So you say that this is a mechanism by a group of people that a group of people can use, but you have yet to demonstrate the existence of this group of people or their identity. And quite frankly, it doesn't sound terribly convincing to me, because I agree that there are problems with peer review. There are issues with and there are issues. Actually, there are issues. Nature, for instance, has this thing called nature communications, and you can, you pay to be published in Nature Communications, which is not the way science ought to work. And I've seen some quite shonky results get published in Nature Communications, and it's not that the people are necessarily, lying. Some of it just isn't science that I think deserves to have the word nature anywhere near it, but it's got the imprimatur. Look, it's published in Nature Communications. Doesn't that sound impressive? Everybody's heard of the journal Nature. It's prestigious, presumably Nature Communications, and Nature are basically prostituting their validation on science that is really quite bodgy, and in some cases, I think, wrong.
I hear you on all that. Well, hold on a second. Let me jump in. I hear you on all that. But actually, I mean, all those things we just discussed, those are all topics that could be gone off into other territories. But the original thing we were talking about, what I was going to say is, and this kind of links into that as well, but you would agree that there's truth and falsity. There is a universal truth. Just start there. That is the case in your mind.
Not in regard to all things, no. So there's a lot of. Are you talking about physical reality?
Well, the reason I just mentioned it, I'll pass the mic here. I'm just bringing it up to say basically this: like, if there is a truth and if there are things that are false, then the most important thing, if one is seeking truth, would be what is true. Meaning, so you can have all kinds of different, groups and systems and bases of knowledge or data that's given to you from government agencies. All of that can exist. Everything can exist. But what is actually true at the end of the day? That's what's key. It doesn't matter how much authority or how much. And so that's the really interesting discussion.
Okay, if I may, I know somebody else was waiting to jump in, but if I can address that. Yes, and I agree that there are imperfections in the system as it is currently done, and then there are indeed corrupt aspects of some aspects of what's going on. But we rely on overall the general mechanism of science is moving in the right direction, and we can kind of tell that by the amount of technological innovation that we've been able to make over the past few hundred years.
Well, what if I were to say that it's just riddled in corruption? How about that?
Okay, well, I would not use the word riddled, but I would say that there are certainly instances of corruption and that we should have better mechanisms in place for detecting those, punishing them and preventing them, because I feel I quite agree. And to my mind, it's you see, for instance, people who are willing to prostitute themselves, who are willing to get up there and say stuff that is scientific nonsense, right? Like, the Earth is only 6,000 years old. You'll see people saying that. Now, if you want to have a religious belief that the Earth is 6,000 years old, go ahead. Religious freedom.
What about a religious belief that a horizontal bends?
Okay, that is a complete mischaracterization of what I said, and I'll thank you not to repeat that error.
If
you want to convince me that you are being intellectually honest in a conversation with me, do not misquote what I said in a simplistic and idiotic fashion.
I didn't misquote anything.
So you are trying to imply that I said that horizontals bend.
No, you said that verticals are not parallel.
Yes.
All right.
Verticals taken at different points are not parallel. Yes.
Okay. So every horizontal to those verticals are...
Every horizontal to those verticals is a straight plane. I don't understand your point. Every plane perpendicular to the horizontal is by definition perpendicular to the horizontal and does not bend. But that is just different from horizontal at a different point, right? So any individual horizontal doesn't bend. And this is the thing that frustrates me here. If you didn't understand what I was saying, 2 hours ago. Why didn't you ask me to clarify what I was saying?
No,
2
all I
hours
was
ago?
saying was you were mischaracterizing somebody saying the Earth is 6,000 years old, whatever, and I just
all right. Are you suggesting that the evidence supports the position that the Earth is 6,000 years old?
I didn't say that at all.
Okay.
I don't give a shit how old it is.
As I was about to say, you can say the world is however old you want, but what you can't say is that the evidence supports any other conclusion other than that the Earth is around 4.6 billion years old.
So,
right? Because
does the evidence?
That's all the evidence supports, right?
Well,
There's
so-
no evidence to the contrary.
Well, so is there any evidence to support that verticals aren't parallel to each other?
Yes. Plenty of it, in fact.
As in?
Again, gravimetry. We can use gravimetry. We can track the trajectory of falling objects relative to other objects. We can we can plot equipotential surfaces across the Earth. We can do, I've been discussing the various measuring techniques that we can use to reconstruct Earth's gravity field for it seems like hours. And you were complaining that I was talking too much, and now it turns out that
I didn't complain.
well, somebody did, and there are multiple evidentiary sources that we can use to reconstruct Earth's gravity field, and to show that equipotential surfaces are not flat, nor are they spherical. In fact, they aren't uniform. They're not even ellipsoidal. They vary a lot.
That doesn't prove anything.
Since objects fall in the vertical, objects move down the direction of maximum decrease in gravitational potential. Right?
So
that's just the physics.
Sorry.
No, go on.
No, I'm saying so you'll have a down and you'll have a straight line as down, but that's the only straight line you'll have.
It only works for down. Only really makes sense for that point. This is the thing about this Allison Bob contradiction that quantum eraser has been going on about. So if you imagine Alice and Bob both on the surface of a sphere walking towards one another, at no point in their path towards one another is either of them moving downwards, right? Because down is towards the center of the Earth, assuming a perfect uniform sphere. In an idealized case, we're going to simplify it, right? But if they're walking on the surface of the sphere, yes, assuming. I mean, this is just a notional. Example, but it's explaining why this isn't the contradiction that QE apparently thinks it to be, because neither Bob nor Alice are moving downwards. As they walk across the sphere, they remain at the same gravitational potential, right? They're not moving downward. If they were moving downward, their gravitational potential would decrease. They're not moving downward because they're moving along the equipotential surface. They're moving along the sphere.
It's
For a
just
perfect
odd.
sphere.
It's just odd you would bring in QE. Where did he come in?
Well, he's been doing a thing about Alice and Bob recently, and I thought that flat earthers would be familiar with the argument, but obviously I was mistaken.
He's barely ever brought that thing up.
Well, I've seen it. Okay, so I don't watch his material, but I've seen him talk about it as presented by other people. So he may have only brought it up once or twice. I have seen him in his inimitable voice discussing this and discussing how inescapable it is and how much of a problem it is for the ball Earth for the ball Earth model, and it's just not. It's not in any sense a problem.
Well, could I ask you
there's
this?
no
How would you make a horizontal line? Like if put physicality to a horizontal line.
You need to just give me a moment. I need to step away from the keyboard for just a moment.
That's fair enough.
I'll be right.
Good morning, everyone.
Yeah, morning, spot on.
What are you doing up, you lot?
I'm up way too late.
What time is it now?
It's like almost 2:30.
Ooh, nice.
Yeah, you're up early though.
I couldn't believe it. I looked in out and I thought, wow, because I came out of this room last night, I sort of just, there's like someone in there. I refreshed it. They're all in there.
This might get interesting.
Bev just went to sleep.
Yeah, Bev
really
passed
good.
out. He said he wasn't going to bed, but he did.
Yeah, you know, you try your hardest, don't you? Eventually it takes hold of your tiredness.
It's like the.
But yeah, it's interesting listening to what you two are talking about.
Yeah, I'm hoping to get a horizontal line out of this.
Okay, so a horizontal line would be a line that extends perpendicularly to the vertical at a particular point, right? So we're talking about a very specific point, and you could build, for instance, if you were careful enough and put enough effort into it, you could indeed make a perfectly horizontal line. Now there are it's a matter of how much accuracy you need.
The spot on. What accuracy would you be okay with?
First of all, I'd just ask the question: when you say horizontal, you refer into a straight line, like without any deviance from any direction.
I'm assuming that's what he means. Yeah.
Yeah.
Rather than a line that is a curve that is coincident with the equipotential surface.
Oh no! We're talking about straight as an arrow, just
straight as an
zero.
Straight as an arrow. Well, I mean, how long do you want this line to be?
Well, it's just something you can, if you've got the last point from which you've got a straight line, whether it's 100 meters or 1 mile. If you continue that straight line, it's just going to be straight. So there's no end to the straightness, is there?
Well, are you talking about constructing a physical line and mathematically constructing a horizontal line?
I would prefer some physicality to it, but
okay. So it's actually that's actually a very difficult process. And for a number of reasons. Okay. I talked about geophysics, and one of the aspects of geophysics that you learn is that on a large enough scale, the Earth is kind of fluid, right? It's not actually stationary. You think it's stationary, and it really isn't. For instance, did you know that there are tides in the solid Earth? For instance, there's a solid. So every day, you will go up by about 20 centimeters, 8 inches or so, and back down.
Well, yeah, when people say the Earth is stationary, they don't mean that. I mean, of course, there's earthquakes, there's obviously movement in some ways of the Earth, but as a whole, it's a stationary surface.
Yeah, so it's well, that depends on what level you want to look at it, right? I mean, so there are mental processes that are ongoing. There are mental processes that are ongoing that are turning thermal energy into vertical motion of the various plates. You're on a plate that is moving, and it's not. You're
hold on. 2 seconds, Tony. We were just talking about creating a straight line, physically. We're not talking about worrying about earthquakes and
well, this is But are you? I mean, if suppose I construct my physical line, and then I move one end of the line a different amount than I move the other end of the line, as would happen as a solid earth tide moves through, as would happen as a solid earth tide moves through, as would happen as a solid earth tide moves through, then it's no longer a straight line. It's no longer a straight line coincident with the horizontal. And indeed, there are sort of temporary changes in Earth's gravity field. If you want to measure precisely enough, for instance, if there's a heavy rainfall and there's water in the ground, gravity is actually slightly higher if you're above the water. If you have a gravimeter below the water, actually gravity is slightly less because the water pulls upward on the gravimeter.
Seems like you're giving a lot of peripherals here. I mean, this is like a lot of this and that, this and that.
Well, this is the thing. Like, how precise do you want it? Right? Because
you're asking questions, but you're not asking the right questions, really. I don't think. I mean, distance. I mean, have you got a distance in mind, Buster?
I mean, I was thinking like 800 meters, straight line, like a horizontal.
Okay, so I mean, you could look at the techniques that they use to construct the tunnels for LIGO, because they address this issue there.
Oh yeah.
So they built these concrete ramps to keep the two tunnels straight, even though the Earth curved underneath them. So you can kind of see the change in elevation relative to the Earth underneath them. Another example would be drag tanks, right? So drag tanks have.
What's a drag tank?
So these are tanks that are used to design the hulls of large ships, so that they're efficient. And what they have is they've got a sort of a ramp that so they've got basically a carriage that drags the hull through the water. But in order to get results that are, because it's only a model and they want it to remain accurate when they scale up, the railing has to actually follow the curvature of the water.
I was kind of more interested in the LIGO tubes.
Yeah. Okay. So you can certainly. There are multiple techniques. I mean, I'm pretty sure there are a couple of but it's a non-trivial engineering accomplishment, depending on how much you've got, and you've also got to consider, what am I making my line with? Because most materials bend under their own weight, right? The force of the force of gravity results in deformation of whatever you're making the line out of. I mean, power lines, you can't make power lines straight. You can't make pieces of string perfectly straight. They sag in the middle. Similarly,
sorry, Tony, just to let you know that you are talking to people in construction here. That's all. Just we use techniques.
Okay. So all right, fair enough. So you know that constructing an 800.
Children.
Okay. Sorry. There's been a bewilderingly wide variety of questions asked me, and sometimes I can be a bit pedantic. But I'm also aware that if I am inaccurate in even the slightest way, you guys, there will be people who will leap on it and try and distort it.
Yeah, fair enough. Sorry, mate. But everyone here knows that. I think everyone here knows that a string line or a rope will sag in the middle. Yeah.
Yes, that's right. So if you're going to make an 800 meter long straight line, you need to look at it. You need to look at what material are you making out of it. Is that material going to remain straight? What are you putting it on? Is that material going to be straight? How compacted in it? How seismically stable is it? is there any water flow underneath that's going to result in any shifting after you've built your straight line? If you're building a structure that is if you're not building a structure that is in contact with the ground, then you've got to account for sag. And if you are building a structure that is in contact with the ground, then the ground moves. There's thermal expansion effects to be taken into account. There's water shifting.
We are talking about 800 meters. Yeah, just remind. Sorry, Tony, I don't mean to butt in, but we are talking about 800 meters here. Right? We're not talking, across continents.
So thermal expansion turns out to be detectable in GPS networks. I don't think it's unreasonable. And again, it's a matter of
Sorry, Tony. If I said that I banged a stake in the ground at point A, first point, and then I was going to move that point to another point. Yeah, are you worried? Are you seriously thinking that surveyors are worried that the Earth is moving underneath these posts that's going to make it inaccurate?
No, what I'm worried about is if you build a large, heavy structure, is the underlying Earth well packed enough to support the weight of that structure, or will it compact under the weight of the structure? That's what I'm worrying about. Does that make sense?
No, it'll just be the top of the post. There's no structure going on. Right? It's just literally
so you want an 800 meter long material, but you understand that soil isn't concrete, right? And there will be, so it's a non-trivial. It depends what accuracy you want, and it depends, how accurate do you want to make, because you can throw a lot of money at this. It's a non-trivial engineering exercise. I think you guys tried looking into the cost of this forcing. It's going to be really, really expensive to do. That's what it means.
That wasn't too bad from when I got it for 600 meters.
Okay, how much deviation was there?
Well, all I was going to say is we actually used a water level to establish a horizontal.
Okay, so under the assumption that water level doesn't change over 600 meters, which is in itself demonstrably false, right? Drag tanks, as I was explaining earlier, are about 500 to 600 meters long, and they have to account for the curvature of the surface of the water in them.
All right, how
much Earth's gravitational field, something like 15 millimeters, I think, something like that. Maybe I got the units wrong. But they have to have a.
I told you it was less. According to them, it was less than 1 millimeter. Do you agree with that?
I wouldn't necessarily dispute it. If the people making the drag tanks say that it's that's fine.
Well, so 150 meters. There's a 0.5 of half of a millimeter.
Yes, well, I was talking about. I was talking about tanks that are 500 to 600 millimeters long, 600 meters long. So, and if you multiply,
the only one I've seen was 400 and something feet, but actually then maybe.
Okay, the largest. Yeah, I think the world's largest might be about 600 meters, but I'm not sure. I think the largest in Europe is about 500 meters. But anyway, these things are very precisely engineered, and they do have to account for curvature in the surface of the water, demonstrating that the claim that there is no demonstrable curve in large standing bodies of water to be false.
Anyone else want to say anything?
But also, I'd like to return to solid earth tides for a moment, because I'd like you to explain solid earth tides to me in the flat earth formulation where gravity isn't a thing.
Flat earth? What do you mean flat
earth? You may be late to the conversation, or you're being deliberately obstructionist, in which case...
I thought we were talking about how we were going to create a horizontal line for 600, 800 meters. So I thought we were talking about.
So the broader context, and I'm saying that there are, I'm not a construction expert, I'm a geophysicist, but I'm saying it depends on what accuracy you want, what time scale you want it done over, what budget you have available for doing this, for undertaking this exercise, and perhaps you're better off asking an engineer these questions rather than me.
Okay. Yeah, if you want that, yeah, no problem. If you think you're up for it, that's cool.
As I say, I'm a geophysicist, not a construction engineer.
So, real quick question: if you end up being involved in, or witness, or observe, or on any level, a physical measurement of the Earth meaning not optical, that indeed indicates its horizontal planar nature, that you're able to verify yourself in this lifetime, what would that then kind of mean for you in terms of everything you've gone through? Like,
so that would suggest to me a number of possibilities that I would have to eradicate, right? So I would have to eradicate the possibility that I was being conned, that I was delusional, that I still had a strong grip on reality. If, after assuring myself of those things, the observation was still in place, then I would want to know about the behavior of the other systems now. Has the behavior of the other systems changed? In other words, has the nature of reality changed? Because it seems unlikely, given the evidence we have available. It's not impossible that new evidence will become available tomorrow, which I think is sort of at the bottom of your question. Is there, if new evidence becomes available, will I change my position? Yes, is the answer, but it would have to be compelling evidence, given the amount of evidence that we have available to us that is consistent with a spheroidal Earth, and only a spheroidal Earth. It would need to be compelling evidence, and the most likely explanation would seem to be that the nature of reality has been altered somehow. That what we thought was and that would be verified by rerunning the old experiments. If we rerun the old experiments and we get a different result, then we're in real trouble. In particular, the geometry of space doesn't seem to make any sense. So I haven't. What I do for a living is I model the orbit of satellites as they orbit around the Earth. And I use the perturbations in these orbits to reconstruct the distribution of mass on Earth's surface. So I create what are called temporal gravity fields. I and my group. It's not a solo effort. Other members of my group use incredibly accurate analyses of GPS data to reconstruct the motion of continental plates and individual GPS sites. In order to do that, they have to reconstruct the geometry of the entire network. So they have to construct the positions of the satellites and the various receivers through time.
But all of that's coming through an authority that you ultimately can't verify. You know, that's the thing. I mean, that's the thing, like, because you can feel how real it is, but if the data is either fabricated or false or purposefully not what they claim it is, the whole thing is just like poof, it's just gone.
Okay, but how do they? Okay, so let me tell you something that we can do with, say, the gravity data. There was a big earthquake off the coast of Japan, massive. I think magnitude 9, the Tohoku earthquake, the one that triggered the Fukushima disaster. We can detect the change in the gravity field from before that event occurred to after that event occurred. And we can do it from data that was made available the day after it happened. And we can compare that with the seismic models of the geometry and the location of the earthquake, which is a completely independent data set. So we can directly compare these two sources of data. Now, if your claim is that that data is faked, somebody has almost instantly worked out what the geometry of the gravity signal should be, faked that for us, and worked out what the geometry of the seismic signal should be, and faked that for all of the seismic stations across the globe. Right? It is inconceivable to me that that a person who has that much instantaneous ability to determine the reality of something vastly quicker than anybody else can, and put out the corresponding gravitational signals. And there are gravitational signals that show up that we didn't know we were going to detect, like events that nobody knew about before we started looking at the data.
I wanted to make a horizontal line, not talk about seismic waves again.
Okay, well, given that I was talking about gravity, I'm fail to see what the hell your comment has to do with the conversation. But thanks for your input.
No. Just wanted to put physicality to a horizontal line.
Okay, get an engineer, talk to them.
Oh, fair enough.
Okay, I'm not an engineer. I'm a geophysicist. I work on Earth's gravity field, and the only reason I'm here is to try and get one person.
You must work with geometry, though. PhD.
Yes. Yes, I do work with geometry. Yeah, and you'd be surprised how little builders care about my understanding of spherical trigonometry. If I went onto a building site and started telling them how to do stuff based on my understanding of spherical trigonometry, I'd cop a brick or a shovel off the backside of the head.
Well, you probably tell someone that the horizontal line is lower at the one end than the other, which may account for that, because in and we've recently so hold on 2 seconds, mate. Recently there's been talk of surveyors surveying up to 300 square miles and treating it like a horizontal plane.
Well, I would say that they've certainly reached the end of where that is valuable by 300 miles. And I'd suggest, well, do it out to 600 miles and see how you go. If the Earth is flat, then it should work indefinitely. If it doesn't work indefinitely, why is that? Again, and since you missed the earlier part of the conversation, my PhD. Since you missed the earlier part of the conversation, I will repeat for you. My PhD thesis was about flat Earth models for the propagation of seismic waves through the Earth, right? And the adaptation of these techniques for viscoelastic perturbations. We use flat Earth models all the time on length scales that are short enough.
How long is short enough? Sorry.
2 degrees, I would suggest that at 2 degrees, 220 kilometers, you're not going to get your flat Earth seismic models to work anymore.
220 kilometers, what, linear, like, distance? Or are you talking like a square there, or like one direction? 220 kilometers.
Yes, 220 kilometers.
Well, and you treat that like some sort of plane in a model.
Okay. Your question was, at what length scale do you think flat Earth models are going to fail? And I said,
well, I didn't ask that. But I didn't ask that.
Okay. Well, what did you ask? Please rephrase the question then.
You haven't got to raise your voice on me. I'm talking to you nicely. I'm not, I can raise my voice and be all like that as well. But I'm not.
Okay, let me, as I have told other people in the chat, you will be under no illusions as to when I'm fired up.
Oh,
okay.
That sounds scary.
So please repeat your question.
I got a quick question first. When you said 300 miles, you mean 300 linear miles or 300 square miles?
Yeah, 300 square miles it was, yeah.
Oh, shit.
Oh, so you
do you understand the difference?
God almighty.
Jesus Christ! Like the 300 square. Fuck's sake,
You
guys!
see the way this is the bullshit you put up with.
What? Go on, no, explain. Sorry, go on.
300 square miles is 17 miles by 17 miles. That's 300
Right,
square miles, right? That's
Okay.
different from 300 miles.
Oh no, sorry, yeah, I meant like actually, yeah, 300
That's fucking
square miles. As
intentionally
in,
misleading.
you know,
That's
17. Sorry, go on.
17 by 17 miles is about 300
yeah.
square miles. Okay,
Right, so 17 miles. There's another, they're treating it like a plane, a horizontal
Over
plane.
that distance, you can probably
yes,
do that.
over that distance, for a lot of purposes, you can get away with doing that. Yes,
well, how far
it's
is hold on? How long is LIGO?
2.5
It's
miles.
about
when you start talking about drop at LIGO at 4 kilometers, then
2.5
2
miles.
kilometers or 4 kilometers. Yeah.
What? And they've got curvature in that, right?
13,200 feet.
You think they've got curvature in that?
Yeah, you can see it.
But the question is not, the question is whether or not it impacts on the angles that the distances that you're inferring from your elevations and your.
I can't believe you said
distances.
that 220 kilometers. That's what you said as a linear distance.
I said that I was absolutely certain that flat Earth models would not be accurate beyond 2 degrees, 220 kilometers.
Yeah, but you gave a
That's what I said.
Distance.
Yes.
Right.
And you're saying that my statement is incorrect, are you?
No, not incorrect.
Because
I'm literally surprised that you said it, because I was working on at that point around 17 and a half linear miles, that's square. So you're talking 220. That's a lot more.
Okay, I am certain you will be surprised to hear, doubtless, that I have not worked on the largest application for which flat Earth seismic models have been used. But I am certain that by 220 kilometers, a flat Earth seismic model will no longer be able to do the job. So I have.
No, but up until then, it would, yeah.
No, that's not what I said.
You'll be
That is not what I said. Okay.
Do you understand? So how much in your model?
Do you understand? Do you understand the concept of English?
No. Do you understand the concept of being friendly?
No, because as far as I can tell,
well,
you're being intellectually. You are being intellectually.
I can talk over you just as bad.
You are being intellectually dishonest. You are being intellectually dishonest. You're being intellectually dishonest.
I'm not being intellectually dishonest. I'm asking you questions.
You are. You lied about the. Okay, so when I say
I'm lying,
listen,
what am I lying about? Go on.
Listen to the words that
I can't talk to you anymore, Tony.
Listen to the words that I am saying.
That's it.
Listen to them. Okay, then fuck off. Right? Good.
Listen, but
what
I'm
I
not
said
talking to you
was.
because you just can't
What
talk
I
to people
said
normally.
was. What I said was, and listen to the individual words and construct them. Beyond 2 degrees distance, that's 220 kilometers, flat Earth models will certainly not be accurate. That is not the same thing as saying that below 220 kilometers, flat Earth models will be accurate. This is like saying, I am certain that there is not a person on Earth who is 100 kilometers tall. That does not mean that there is a person on Earth who is 99 kilometers tall. They are not synonymous sentences, and you are deliberately misinterpreting what I am saying.
So there's a distance to what can be interpreted.
There is a limit. There's a limit over which the flat Earth model is quite accurate enough, sufficient for many purposes. And this is why we have them. We develop them. The mathematics is a lot simpler.
What's the cutoff limit? What's the cutoff limit?
Somewhere below 2 degrees. I'm not going to
degrees.
specify. I'm 220 kilometers.
See,
138 miles.
Yeah, 38 miles, man. So
somewhere below
everything...
that.
You realize Tony's talking about seismic models here.
Yes.
we originally wanted to make a horizontal line, and it always seems to go back to seismic models, and I don't know the connection.
You want to build a model. Talk to an engineer. How many times do I need to say it?
Well, even with your seismic models, you show graphs in a linear horizontal manner.
Those are schematics.
In a horizontal linear function.
Oh,
you're looking at cartoons. Come on.
I didn't present them. He did.
I know. I'm just telling you.
In the
recognize what he presented as a cartoon. Come on now.
In the I presented what I presented in the hope that it would be educational, not that people would instantly interpret a schematic cartoon as a documentary of real life. Do you think bears can talk?
I didn't present them.
I'm presenting a schematic. Do you know what a schematic is?
Yeah, it's supposed to represent something.
Yes, it represents the propagation of a sound wave or a physical wave
in a horizontal linear function.
If you perturb a horizontal linear body at one of its ends, so imagine a girder and hitting the girder with a thumping great mallet that is bigger than the girder.
I wouldn't do that.
Well, good for you.
I mean, I would want all my stuff to match up. I mean,
well, you see, what we do is because the concepts are so complicated, we tend not to go into the deep end where the slack-jawed yokels just look at us blankly and say, what the fuck are you talking about? And we tend to start with a somewhat similar example. And we rely on the fact that the students possess sufficient mental agility to take the basic principle and adapt it to a more general circumstance. That's how education normally works.
Generally, as in 220 kilometers?
Except, of course, in your case.
I just wanted to bring physicality to a horizontal line.
Okay, well, good for you.
Yeah, I mean, go to engineer. Fair enough. Whatever.
Okay, let me show you what happens physically on the Earth as far as earthquake propagation is concerned, since you seem to be having an enormous problem with the various concepts. Well, let me bring this up.
800 meters of anything is a damn noodle.
Yes, it is a damn noodle. You can, if you are precise enough, get it accurate.
Noodle is in
it's going to have to be supported very regularly.
It's going to deform under its own weight.
Everything does.
You couldn't just make some marks on posts?
Well, what do you use to make the marks on the post? That's the problem.
Relative to what?
I'm asking.
You won't trust you won't
what about
trust
the tools that surveyors use, Blue?
Well,
the auto lights?
Yeah, you could use
site level, auto level.
Or auto level. You can use either one.
Or even better, a water level.
Water level. Going to establish level at 2 points, equal potential at 2 points, each end of it.
Yeah.
Now, if you
except it won't. We've already demonstrated this. Again, you can have it. If you can have an 800 meter.
Sorry, PhD Tony. Blue was talking, please.
Yeah, sorry. Okay, go ahead.
Well, if you put a point, if you put a point in the center of the water level, and then you shoot that from end to end, You're going to see the center of that thing higher.
Yeah, but
than
you never. No one ever does that, Blue. No one goes to the middle to find out what the level of the two endpoints are, because that's ridiculous. Otherwise, you just move one end to that point and check it, wouldn't you? In reality, because that's where we all work.
Yeah, you can do that. You can
Us
do that.
people work
Which is
in
what's
reality.
been wrong. Which is what's been wrong with Bell's test all along. It doesn't prove anything. It doesn't prove that the Earth is
What
round.
what happens if you've got a straight line? What about a shared line segment in the middle?
What you've got to have is a way to look at all the way from one end to the other. That is the straight line.
Oh, you don't sight down a water level.
Can't do that.
Do you understand the geometric principle of the shared line segment in the center?
Do is step yourself right around the curve.
Do you actually understand that, though? Do you understand the principle?
What I understand is you're using a water level to prove that water is level. Thank you. We already know that.
Do you know the principle of the straight line segment?
I know
in the center.
Principle of the straight line segment in the center, which proves nothing. Yes.
Yeah, in the test. Do you know the test?
Nothing.
Is what I'm asking.
Yeah. Yeah, and I know that you're not looking from one end of that 800 meters to the other end of it.
Wait,
why have you got to look across it like that?
You've got
and you know that you're looking at them right in front of you.
You've got no other straight reference. The only point you're looking for is the difference in the height of that thing at the center.
No, wait a minute. Wait a minute.
Yeah, go on.
Sorry. Point to point, one point to another point. Would you agree to a straight line, no curvature, not deviating in any direction?
That's all you've proven is that you can.
No, wait a minute. Point to point. Just 1 to 2, point to point, straight line, right?
Yep, gotcha.
Okay. 2 to 3, straight line.
Different straight line.
3 to 4.
No,
wait a minute.
Different.
Yeah, but wait a minute. When you get to where you start overlapping,
doesn't matter how much you overlap them.
What do you mean it doesn't matter?
You can put them parallel to each other, and they'll be exactly the same. But you start overlapping them, you're just moving. You're stepping yourself around the curvature.
So you're overlapping parallel lines, and they're parallel.
They're not parallel.
You just said they're parallel.
They will not be. No, I did not. I did not.
At no stage did Blue say parallel.
If you have point-to-point references and you overlap them, they have to be parallel.
No,
No, they don't.
How can they not be?
Hey, hold on then. 2 seconds then. Why? Like, in reality, again, like in construction, has anyone ever measured a horizontal that isn't parallel to the other horizontal that they made? Or a continuation of the other previous horizontals that surveyors placed there?
You don't need to be that accurate when you're constructing most structures, right?
Well, it's a good job that you're not in construction then, Tony, because the people that are, and there's a few in this room I know, like have to specifically, be accurate because of things like drainage and, you need to know if there's a fall in the land. Yeah. You need to know all these things. You have to be really accurate. Yep.
Yeah, as opposed to people who measure the speed at which continental plates drift. They can just fucking wing it, right?
No. I had to watch a guy the other day just transfer a horizontal for over a mile from a monument to get the elevation for a house to be above floodplain.
Did he use differential leveling to do that?
Well, yeah.
Mm-hmm. Do you know why?
He had to get parallel horizontals.
No.
Oh, he had to get
leveling works because the drop to the
horizontals intersect
is exactly the same as the drop
because horizontals intersect.
You say it, but we want to see some proof of that, please.
Well, in fact,
you don't need to see any proof because every single time I've ever done a plumb line or a horizontal or a vertical, they're always perfect. Every single one that I've made in probably about 30 years of construction.
If you open that up, you'll see.
Yeah.
Well, I got you.
Open that up. What? How are you going to check? How are you going to check that one isn't parallel to the other?
You ever model a satellite of it?
You know what I've got? I've got something you ain't got. I got the
Go on,
mute
then,
button,
go.
so stop over talking me, okay?
Yeah, sorry, Blue. I didn't mean to. I sort of was. Yeah,
You can open
carry
up. You can open up the or expand the little picture that Terry put in the chat there a minute ago at 232. That's LIGO.
Oh, sorry,
okay?
I haven't really been looking.
That's LIGO. That's LIGO Livingston. That's That's actually my drawing. Well, that's taken straight off the as-built drawings. Now take a look at that. These are elevations. These are the actual elevations of the pad that the tube is sitting on. Look at the upper one.
The pads in which the tube is sitting on, that got spoke about earlier, though, didn't it? Where they can be adjustable. The pads are there just purely to put the thing on, right?
Let me ask you why would they intentionally pour these pads so that they're a foot low in the middle?
So that they can use the
like, seriously,
bubble
mate,
level and level it and be curved.
Can you actually tell me why they would do that and why it just coincidentally matches the curvature of the Earth?
So they can use a coincidence level and level it, and so the laser will curve.
What?
I just posted a thing from the LIGO arms. They use the coincidence level to line the tubes.
I posted a thing earlier that says they did differential GPS.
I just posted one that says they used the coincidence level to line the tubes.
Well, I'll take a look at that in a minute. Look at those elevations. 64 feet, 64.09 one end, 64.12 the other end, 63 in the middle. Now, you guys have been in construction 30 years. I did it for 45.
Yeah. Well, they obviously put the pad in, like, they either made a mistake and it was a foot lower than the rest,
Obviously, yeah, they made a mistake on that one, right? It's a foot lower in the middle, so they fucked up. Now look at the other one, 64.12 on one end, 60 on the other end. Let's just round these off and make it easy. 60 and 64. That's 4 feet. It's an elevation change of 4 feet. At the center point, that would be a 2-foot elevation change. It should be 62 feet.
Well, that's cool.
It's 61 feet.
Well, that's cool.
Low. They fucked up again, didn't they?
That's cool because
you go to
they
Hanover
leveled the
site in
tubes with the coincidence,
and it does exactly the same thing.
Well, that's cool because
doesn't
they
matter
use
about
the
the base.
coincidence.
It just as long as the tube and the laser.
I know.
Are
Any
accurate.
port in a storm. Now, where's this thing?
Hey, you guys
Hold
seriously
on. You're telling.
You guys seriously think that because you know how to level a patch of ground, 100 meters or so wide, you're going to lecture somebody who works on the shape of the Earth?
Lecture?
As
no,
their profession. Okay, well,
you're the
then
one lecturing.
Allow me. Yes, I'm lecturing.
You're like projecting
because I'm
basically.
the one.
You're saying that we're lecturing you when you're lecturing us. Yeah, nice.
But you think you're in a position to say the Earth doesn't curve?
No, I'm not saying that.
We
at all.
know.
I'm saying that horizontal is a straight line, and that.
Yes, it is. Yeah, horizontal is a straight line. Well done, you. Okay, let's look at.
Is LIGO horizontal?
I believe they've made every effort possible to make sure that
it's the straightest thing in the universe. So I've been told. So are you saying that they're bending it 4 foot at one end? Are you serious?
It may be.
Because I just like this. Someone's said to me something in the chat I hadn't really seen before. Brad, the science guy's done a drawing of like some curves, water levels. I mean, that's just absolutely insane. By the way.
All right, the thing I posted in there, in as a counterpoint to what you're talking about with a level. This is how they actually leveled it. Okay, it's called precision alignment of the LIGO 4-kilometer arms using differential frequency, differential GPS. I'm sorry, dual frequency, differential GPS.
Got the same. What I just posted came from that same PDF where they use. I'm looking at PDF. Let me go to the top of it. Precision alignment of LIGO 4-kilometer arms using dual frequency differential global positioning system in the same.
Did you read this?
Yes, that I have.
No, you didn't. You haven't had enough time to read it.
Earlier today, I mean, we've been going through this since 12 hours ago, and I pulled this same image that I put up that uses a coincidence level. That came from the same documentation. They have to level everything, but you think level is something other than horizontal.
Yeah, hold on then. So sorry, Buster. I'm just sort of catching up on some of these in the live chat, and obviously Brad, the science guy's been doing loads of pictures about.
What page in the PDF? You're saying you got that image that you put up from the PDF.
It says
what
July.
page on the PDF? What
This
PDF?
says-
What page of the PDF is?
Page 38, Tony.
Page 38.
You're 6.
Okay. Yep. Okay.
I'm gonna go search for that and see what they say about that.
Brad, can you see the problem with that? That the way that you've drawn them like that on a slope. You know what I mean? That doesn't like make any sense, because if you're looking from one end to the other and it's dropping away, surely at the other end, if you were looking back the other way, you'd think that the other end was dropping away. So either one is lower than the other or not. You know, which way is that? That's just crazy. But anyway, let's move on, because that's just like some sort of kiddie drawing.
No, the Equipotential Service. Okay, so we had some complaints about, I only showed seismic waves in a cartoon. So let's go and have a look at some seismic results from an actual earthquake, shall we? So in this
on your is this on your flat Earth model, or is it on a?
So what I've taken is there was an earthquake at the Macquarie Rise, which is shown as a red star on Christmas Eve 2004.
What? Sorry, can you say that again?
Macquarie Rise.
Quarry Rise?
Macquarie Rise. Macquarie. Rise.
Yeah, what is it? Sorry, I didn't catch what it is. I didn't get the whole thing. You're just repeating a word that I don't know what it is.
Okay, then instead of asking what I said, and me just repeating it ad nauseum, let's clarify what you're asking, which is an underwater plateau south of New Zealand.
Underwater plateau. All right, yeah.
Yes.
So like a plane under the sea, yeah.
Yes, like a plane.
Yeah. Can you repeat the spelling of that so I can write it down? I'll have a look at that. Thanks.
Macquarie. Rise, R-I-S-E. It is near Macquarie Island, Macquarie Island. It is to the south of New Zealand. Anyway, there was a magnitude 8 earthquake on Christmas Eve 2004. Okay. And we're looking at in an azimuthal equidistant projection centered on the epicenter of the earthquake, which is represented by a red star. Okay, so the red star is just over the earthquake. The blue circles are going to be where the earthquake signal most recently arrived, and they're going to slowly sort of expand out from there. So this is the first pickup in the analysis that I was able to do, which was in Auckland. Okay.
Sorry, where's this picture? Or where's this document?
So am I not sharing my screen?
Oh, sorry, you're sharing. Sorry. Let's have a look.
Okay, so we're about 3 minutes after the earthquake, and the blue circle represents the first arrival of seismic energy at Auckland, and we're going to mark the stations as they first receive the seismic energy. Okay, we're just moving through now. Now it's arrived in Melbourne and Adelaide, Sydney, You can see it's just hit Antarctica.
These places where you've got sensors set up.
Yes, these are places where we've got seismic arrays, and there's the one at the southern pole that I was talking about. And you can see that the seismic energy here is radiating in all directions, but it's radiating as a circle. Now, we're limited a little bit because we don't have complete coverage, but you'll be able to see the circular nature of the wave pattern as it starts hitting more densely populated areas.
Mm-hmm.
Like North America, you can see that it's spreading out in a circle from one side to the other, and that's and this is the pattern that we observe for every earthquake. If you just plot up the
okay. So what does that? So what are you trying to explain there? I mean, yeah, something.
What I
am
am trying,
and everything goes away from it, right? Yeah.
Yeah. So the seismic energy radiates away from it like ripples from a pond. So now we're going to try the same trick, except we're going to use the Azimuthal Equidistant Map. And you can already start to see the problem reasonably early on, which is to say that the seismic energy gets from one side of Antarctica to the other side of Antarctica very, very rapidly before it's gotten to the center of the Earth. And this is a rather bizarre set of behavior. Rather than spreading out like a ripple, as one would expect, it actually seems to be closing in a circular path on the point opposite Macquarie Rise, if the Earth were a sphere, or the point that would be opposite. And so, this is just one earthquake, right? And this is just one, and these are just the first arrival times. This is just the time when the seismic energy first arrives at each of the stations, plotted up, and there's vastly more data we can use with different phases. We just saw the shadow zone of the P waves kick in there. That's why there was that gap. But now we've got tens of thousands of events, tens of thousands of seismic events, and tens of thousands of stations. And for every combination of seismic event and station, the energy spreads out like that. It spreads out in a circle away from the epicenter, around the other side, and then it comes back. It comes back around the far side of the planet and it closes back in on where it started from. And you can't do that on a flat Earth. It just isn't possible, right? The Earth cannot be flat and seismic energy behave in this way. It isn't physically possible. And if you want me to accept that it is physically possible, you're going to have to put some work in and show it, right? And you're going to have.
Like, I'm too familiar with that before. I've never seen that particular, thing. So I mean, yeah, is that a video on YouTube, or is it your own, or what?
That's my video, and it is on my channel on YouTube. Yes.
Yeah, so I'll have a look later at some point. Yeah. Okay.
Okay. So
you're just taking information from different points on Earth.
Yes.
And they're timed, and they've got like a scale, and you're now plotting it on a on a globe.
That's right. Yes.
And you think it works better on a globe than a flat Earth? Is that what you're saying?
Yes. In fact, I'm saying that it only works on a globe and that it doesn't work on a flat Earth.
Well, I mean, I don't know who you were directing all that to, if it was just me or not. But I mean, yeah, I don't know anything about that. It's like I'm literally just the guy saying that horizontal straight. That's what I'm saying.
So my question to you, my question to you then is, do you accept that the Earth is spheroidal? Because I just showed evidence suggesting that it is.
You've shown me
models. This is evidence.
You show me computer images of models
from a flat
map. Okay. Yes, all maps are flat. That's the definition. Well done, you. But they're also projections. Again, we're going through this like, and it's like talking to the.
Wow.
It's like what? Sorry, cut out.
He just dropped.
I don't know what to say really. I mean, I've just got up and I'm like, I thought we were talking about construction and straight lines, and now we're talking about seismic waves and models again.
Okay, so is this about the shape of the Earth, or is it not?
Shape?
Not shape, mate. No.
Okay.
We're just trying to establish.
You're claiming that the Earth doesn't have a shape, then?
I don't know, mate. All I'm saying is that water. If you look at what science, whatever his name is, Brad, has done those drawings with water levels. In reality, that doesn't work. Like literally, it's just completely. It's geometrically impossible
Would
to happen.
Would you accept the statement that water and all fluids conform to the geometry of the forces applied to them? They move in response to the forces applied to them.
Hydrostatic equilibrium.
Yeah, exactly.
Yes. Yeah. So
we're talking about bodies at rest here, Tony.
Yes.
Bodies like a canal. Now, yeah, that would be a great place to...
given that you understand how buildings work, you understand that there are forces in operation even when something is not moving, right? So there is a downward force being applied to the elements of structures that you build, even though the building is not falling over. Do you agree to this point?
Yeah, you get a vertical, horizontal, the perpendicular, and you make another horizontal.
Okay, so we are all familiar.
Perpendicular to the horizontal.
We are all familiar with the concept that something can be experiencing a force but not moving in response to that force because that force is offset by other forces. This is not an alien concept to anybody in this chat, is it?
What do you mean offset by forces?
Okay.
Well, all I'm saying is you said you build houses. We know they're built plumb and vertical, and then so if things are falling down on the vector of down, which is like perpendicular to horizontal as well, then that's why houses stay where they are when we build them, because they're all like, unless you've got if you corbelled a bit of brickwork out and you didn't, it wasn't done correctly, it'll just fall off the building, right? So we know all about like what things do when they fall. So I don't need to be schooled on that.
So the fact that water in a canal is not moving vertically does not mean that there is no downward force being applied to it, does it?
Well, there's
it's just being offset by the reaction force at the bottom. We are going through
hydrostatic
equilibrium. Sorry.
Okay. Gravity.
It's a cause, not an effect.
That question makes absolutely no sense whatsoever. So
is it the cause or the effect, or is it both?
Of what? Is it the cause of what or the effect of what?
It's the downward vector. Is there
the downward vector of what?
Vertical to the horizontal, perpendicular.
Do you mean the direction in which things fall? Is the direction in which things fall the result of gravity? Is that your question?
No, I just asked. You keep invoking gravity. Is it a cause or an effect?
Okay. That is a meaningless question. Ask a more meaningful.
No, it's not.
No, it's not.
What are you suggesting is cause?
Like, if the water is at rest in a canal, yeah, then it's at rest in a canal. Everyone knows about hydrostatic equilibrium. If you leave it, it will establish a level. Yeah?
Yep.
Right.
Horizontal at all points through a connected fluid.
Yes.
Brilliant.
Okay, but horizontal is different as you move from point to point.
So that's what we, like 3 hours ago, I said bendizontal and you gave me a hard time.
Because that word has no fucking meaning whatsoever.
You're saying horizontals are different.
Bendizontal does not have any meaning.
Okay, well, your horizontals are different all along those points.
Yes. Yep, absolutely.
Okay, so they're different. So different zontals.
Nope. I don't know why you think, redesigning the English language to support your ideology is going to work.
Oh well, you should have a word with B-ball because he wants to say that triangles can have more than.
I don't even. Well, they can. Spherical triangles have more than 180 degrees.
You're redefining the English language.
No, I'm not. Look up the term spherical angle. Go and Google it.
Well, a triangle only has an interior angles of 180
No, it isn't. A
degrees.
triangle. That's a rectilinear triangle as opposed to a spherical triangle. Look up the term spherical triangle. It's a perfectly well-defined term.
You will just redefine it.
No, I am using I have literally done nothing. This definition existed before I was born. This definition will continue to exist after I die. I have done nothing. I am the definition of a spherical triangle, the definition of a spherical angle. Those definitions.
The only spherical thing about it is you've got a triangle that's 180 degrees, and you bend some of the angles.
No.
Yes, you do, because in reality, there are only 3 points to make the triangle, yeah?
Yes, that's right.
There's nothing more than that. You can't have any more than 180 degrees in a triangle.
3 coplanar points.
Yes, you can. Yes, you can. It's called a spherical triangle. Look it up.
Well, how can you have 3 coplanar points and it's a triangle, but then the angles are more?
Spherical triangles the points of the spherical triangle.
How do you measure an angle from a curved line?
How can you have angles with more than 180 degrees in a triangle and it's in the same plane?
Which question do you want answered first?
No, I want
the one that makes sense or the last one?
No, I want you to answer why a triangle only has 180 degrees and they lie in the same plane.
That would be a rectilinear triangle. Yes.
Okay, well then you're redefining a triangle if it has more than 180 degrees.
No, I am not. And you can say that I am, you're just wrong. And since you refuse to go and look up the term spherical triangle, you refuse to even Google it, you refuse to even look on Wikipedia to see what it says about spherical triangles, right? You refuse to do any of that. You're just going to sit here and say you're redefining triangle because there's no such thing as a spherical triangle.
They use 180 degree triangles, that's why.
No, they don't. They use spherical excess. On any large scale,
after the measurement has been taken.
No.
Look
at the measurement and they get.
Like seriously, like hold on, I've got a little thing for you to do. Right, if you're stood on a mountain, yeah, and there's someone stood on another mountain like 100 miles away, let's say, and there's another one over there, and 100 miles away, and there's 3 points, yeah. You're all at the same elevation. They're all these tops of these mountains are perfectly at the same elevation, horizontal, yeah. So those 3 points make 180 degrees. Do you agree with that?
Yes. Yep. Those 3 points make 180 degrees if you've got direct line of sight. But those are not spherical angles.
So if you've got line of sight, then they are 180 degrees. Do you agree with that? Yeah.
Yes. If you're working in a flat plane.
So the only time that you bring in this other spherical excess is when you can't see the thing you're aiming at.
When you're looking over distances large enough that the curvature, you'll detect it all the time if you're precise.
No, but are you actually measuring something you can't see then?
No.
Right, so you can see it then. There's line of sight then. Is that what you're saying?
That's the point. That's the point of the intermediate surveying, right? You survey to intermediate points.
Generally, surveying, you only survey the things you can see. So, yeah, we'll go with that.
No, so generally when you're constructing a map, right, a large-scale map of a region, where you can't see all of it at the same time, okay, you progress along the surface of the Earth, taking measurements as you go, right, from one point that you can see to the next point that you can see, and so on and so forth.
Yeah, you set a baseline.
Yeah. Yes, you set up a baseline, and
that's a straight line, isn't it?
No, that's a
so there's definitely no excess on that line, is there?
Well, it's a line. It's not a triangle.
Exactly. So there's no axis in that line.
That's not true at all. You haven't constructed your triangle yet. You've only got
that line isn't curving.
No, it is curving. If it's moving along the surface of a sphere, by definition, it's curving.
Oh, you had to everything's presupposing.
Well, you need to take the angles and look at them, and then make them work without the Earth being spherical.
You can't have an angle unless it's a straight line.
That is absolutely untrue. Look up the term dihedral angle.
You try and measure an internal angle of something that's
look up the term dihedral angle.
I did, and it's planes.
Yes,
plain
it's
straight
the planes
lines.
that coincident. It's the planes that are coincident with the curves, right?
Yeah, they're
it's
planes.
the angle between the planes. So you can. That's how the angle between the curves is defined.
But they're planes. They're straight lines.
Planes are not lines. Your line.
Planes
are not lines.
At any point
a line,
that lies along the plane.
A line is a one-dimensional.
Planar points. Yeah? Only 3 points. Yeah.
Yeah.
3 points define a plane. Yes.
Yeah.
Yeah. We all know this. You know.
Yes.
Once it's on a sphere, you don't have.
Don't tell me. So, yes, you do. But
let's calm it down a bit again. Let's calm down again because it gets heated. I don't want to get heated.
Fair enough.
Because okay, so did any of you even bother to look up spherical triangles?
Dude, the only way you can have a triangle is three.
Even one of
3 points.
Did even one of you bother to do that?
Oh, come on, Buster! Come on, carry on, mate. Sorry, I couldn't hear what you said.
Sorry.
No, you, Buster. You know, he was just shouting over the top of you again.
No, 3 points. 3 points define a plane, right?
Mm-hmm.
Yes.
Yeah. And your dihedral planes, either one of those dihedral planes, 3 points on one of those planes defines the plane.
Yeah. So?
Well, they have to be straight lines between those points, right?
No.
No.
It's a plane. It's defining a plane, not a line.
3 points
you guys
on the plane.
Do you think a plane? A plane is like
I can hold up 3 fingers.
Yes, I know what a plane is. Thank you.
I can hold 3 fingers up in the air and
well, you said something about the curving.
I've defined a plane with my fingers.
Okay.
I don't need any lines between
There's
my fingers.
Points that lie in a plane, and any 3 points define a plane.
Yes. Yes. Well, actually, that's not true.
On that plane.
That's not true.
In Euclidean geometry. Yeah.
No, it's not even true in Euclidean geometry. You need 3 points that aren't collinear.
Aren't collinear.
If all of your points lie on the same straight line, then you're not defining a unique plane. You need 3 points that are not collinear to define a plane.
You are correct. And corrected.
But those 3 points to define a plane would be a triangle with 180 degrees?
Yes.
Okay.
Right, good. Thank you for that.
Okay, but if you take 3 points on the surface of a sphere, they form, and let's say one of them is where we're measuring our angle. Okay, you've got 3 points. You've got your point A that we're starting from, and there's B over there, and there's C over there. Okay, so you've got 2 great circles, one from A to B.
Now you're switching geometries.
That's what we're talking about.
We're allowed to actually, I haven't asserted that the Earth is a fucking sphere yet, have I? I'm just explaining the geometry on a sphere.
No.
Do you think that's out of line?
No, yeah, it is, because you don't play Uno and Monopoly together. You don't mix games.
What you're saying is that we cannot consider a sphere because you've outlawed it.
when definitions change, you have to switch totally.
The definition of spherical angle has never. The definition of spherical angle has not changed.
Spherical
It's
angle.
always been.
What geometry is that from, though? You know, like, I mean, we know what a triangle is like in Euclidean, yeah?
Yes, and it would.
And it's backed up by axioms and actual proof, yeah? Real proof. In reality, like, I could draw a triangle, I do it all the time. I set out a building literally last week, yeah? And I used 3, 4, 5 to check the to check that it was square. Right? That's reality.
Is it? Yeah. What was the accuracy on your 3, 4, 5 triangle?
3, 4,
What was the accuracy? What was the accuracy on the measurements of your 3, 4, 5? Very accurate. Oh well, you know, how accurate? 10 to the minus 9 meters.
9 minutes. You're going
10 to the minus 9 meters.
No, all I was going to say is it was square. Yeah, it measured the diagonals.
Okay, like, to what accuracy? To 0.1 of a degree? Was it absolutely spot on? You're saying that this is exactly 90 degrees. But both.
Well, yeah. Otherwise, it wouldn't be square, would it?
So you're saying that that's exactly 90 degrees. There was no deviation from a straight line in either surface, and they met at exactly 0 difference. There's not even the tiniest of error, not even 100th of a degree error in your angle.
Well, when you talk about degrees and hundredths of degrees, I'm talking about just setting out a square. That's it. Like you don't think that I can set out a square on the floor?
I'm saying that there is a limit to the accuracy with which you can set out a square on a floor. And if you don't understand the concept of accuracy, okay, here are two. When you measure the distance between 2 points,
is LIGO 90 degrees at the apex?
It is really close. It's as close as they
can. Is it close or is it accurate? Come on.
It's really close.
Okay, what is the difference between close and accurate in your...
I don't care. I'm just saying, is it 90 degrees or not?
Yes.
Right. So they were able to construct LIGO at 90 degrees.
As I recall, it's off a few arc seconds.
They constructed
Sorry, Blue, I can't hear what you're saying, mate. Sorry.
As I recall, it's off just a few arc seconds. It's in the literature.
Oh, so it's off
someplace.
Yes. Almost everything is, mate. Nothing's exact. This is going to blow your mind.
I can't believe that they would have made LIGO not square.
By the way, let me interrupt for a second. Please read page 10 of that document that you pull that figure out of. You'll find out what they used the coincidence level for. It was not for aligning the damn tubes.
It's sitting on top of them.
Used it to plumb that fixture.
Well, you know,
all of the alignment was done with GPS.
So you seem to have a problem with the idea that everything is approximate, right? Nothing is perfect in reality.
Let me ask you this: how big a room?
You just switch that.
You squaring up?
I'm saying everything is accurate.
Did you use a 3, 4, 5? What? 3 meters by 4 meters by 5 meters? Is that what you did?
It's something like, well, you know, you get a 3, 4, 5 in the corner, and then you just check your diagonals, right? If you check your diagonals out external measurements, and they're exactly the same.
All right.
Yeah.
3, 4, 5. How big was the room?
I think it was probably about 12 meters long by 4.5 meters out, something like that.
Was that accurate to the nanometer?
It was square. Yeah, the same measurement on each diagonal. Yeah.
You seem to be having trouble. Do you know how accuracies are represented?
Yeah, on drawings that say this is the measurement of the diagonal. Yeah, and that's
okay. When you measure something with a tape measure, right? Yeah. Or how accurate do you think that is?
Absolutely bang on, mate.
Yeah. Let's flip the script.
There's no thermal expansion of the
tape measure. No.
Let's flip the script. How accurate can you be with your?
There's no
strain. Are you serious?
There's no strain deformation.
An expansion of a metal tape.
Yes.
Measure on a basketball. Okay.
Let's flip the script. How accurate can you be with your curved angles?
Expansion of that metal tape is
How accurate can you be with your curved angles?
Well, we can be pretty accurate. Accurate enough to recognize that there is an unmistakable spherical excess.
What's spherical excess?
Okay, I suggest you go away and read it. Since you've been arguing, you've been arguing this point for the last 2 hours, and you haven't even bothered to familiarize yourself with even the basics of the argument.
I have.
Well, then why are you asking a stupid question?
Because you can't explain it.
Yes, I can. I'm not going to, because you're a dick.
Oh, thanks.
You're welcome.
That's awesome. Great. That's awesome response.
Oh shit! I cut out there. I missed that. What was that?
You cannot have a triangle on a sphere that does not have more than 180 degrees.
Great, magical. That's fantastic.
It's not magical. Do it yourself.
Well, that's what I'm saying. Once you
is the amount is the
three points on a plane.
We're talking about on the surface of a sphere.
Oh,
right.
Well,
So
once
you draw a line on that,
is the angle in excess of 180 degrees.
3 points.
3 points on a sphere cannot be 180 degrees. You cannot.
You just got to bubble them.
You
bubble
cannot
them out.
form.
Bubble them out.
You cannot form a triangle with 180 degrees.
Yeah, because you can't have
a sphere.
because you can't have straight lines. So
impossible. No,
you can't have straight lines.
But you can have angles.
You
can't have angles if you don't have straight lines.
Yes, you can, because you have coplanar, because you have planes that coincide with each of the great circles.
Once you do anything on the surface of a sphere, once you do anything on a surface of a sphere, anything on a curved surface, you draw whatever you want on it. That's curved because it's curved.
Yes,
they're 2D.
Yes, we know that.
Yep, exactly.
You know why we know that?
Thank you.
We know that because spheres are curved. We know that.
Look at the animation here. Okay, you go down the animation that is currently occurring from Anamorphic Mind that is currently going on in the chat. 3 right-angled triangles, and we're back to where we started. That's a triangle on a sphere. You know why it's a triangle? Because it's a shape with 3 points with 3 internal angles, hence the name triangle. A planar triangle is a subclass of the more general triangle. Spherical triangles are a specialization. It's not redefining. It's you being ignorant.
You being ignorant
of the term. You being ignorant of a term does not mean that the term does not have any validity.
I think you should yell more.
That works better.
Well, you see, I've introduced evidence for gravity. I've introduced evidence for seismic waves. I've introduced evidence about spherical geometry, and all you say is nah in various forms. And I've determined that all of you are just dicks, right? At this point, not one of you can qualify as an intellectually honest interlocutor. So,
what?
Intellectual honest interlocutor. Look it up. Locator. Interlocutor. It's all one word.
Okay. I'm just asking.
Well,
I just try to figure out how you have depth to a 2D thing. So doesn't make sense.
That's what I was saying. That's what I was trying to point out. You got 3 points in a plane. How do you have depth to it?
I don't know. It's conceptual. It's only conceptual.
But the conceptual. Let's treat it as a conceptual thing. Why does the conceptual stuff agree so well with the actual observations on the Earth. You know, you need to go out there and you need to do these surveys over 300 kilometers and prove us wrong. Because we've done it and we've gotten results that prove the Earth is spheroidal. You want to prove that it's flat? Go out there, do it yourself.
So who's
we? As in mainstream science.
Ooh, I am an interlocutor. I do take part in dialogue and conversation.
Yes, you're just not an intellectually honest one.
I try to be.
Well, you're failing.
How?
Because you are not even trying to learn basic elements.
Well, he just looked up the definition of a word that we didn't know.
Yeah.
Yeah. Did he look up? Did he look up spherical triangles? Did he look up spherical angles?
Yeah, I think that's
I've done that multiple times. Yeah.
Yeah.
Okay, so what's the problem here? You keep on saying you can't have angles. You can't have angles on a sphere, and yet you go and you look, and they tell you that you can. Because point
to point is a straight line with no curvature.
No, it isn't.
And then
Not
3
on a sphere.
points.
It isn't.
Oh,
not on a sphere.
If you want to 2D think, then go right ahead.
On a sphere, point to point arcs are geodesics. Now,
a straight line on a sphere would be a chord.
Yes, exactly. Well, it wouldn't be on a sphere. It would be inside a sphere.
That'd be Euclidean.
Yeah. Right. So the point is that straight line geometry works well enough when you're looking at this side of the building to that side of the building. But once you start getting up to significant distances, and we've built stuff over significant distances, like railroads and highway systems, and submarine cables, so we know how distances work on these. It turns out that your straight line stuff doesn't give the right result. So we give away the straight line stuff and we say maybe there's another geometry.
You give away the straight lines?
Yes, we say, well, obviously this distance doesn't correspond to a straight line distance, but it does agree very well with the spherical distance.
What's a spherical distance?
Were you here when I was explaining the angular distance between 2 points of known latitude and longitude earlier?
So you're having a curved straight line?
No.
I'm confused.
Yes, obviously, but that is no longer my problem. I explained to you earlier what a spherical distance was. If you weren't paying attention, that's on you.
Point to point is a straight line with no curvature.
Not if you're constrained to follow the surface of a curved body. It isn't.
How do you use that practically?
You use that practically, for instance, when calculating how much fuel you need to put in your jet so that you will land at the point that you want to get to, as opposed to some other point that is randomly chosen because you put the wrong amount of fuel in because you listen to a flat earther.
Come on. Seriously?
A straight line can be described as curved.
Wow.
So
yes. Yeah,
I don't understand.
I can describe my dog as a cat too. It's a
No,
conceptual.
but straight lines can be described as curved. It just depends on your perspective of viewing what that straight line is.
That's brilliant, because next time you want a retaining wall, call me, because I'm just gonna lay it with the contours of the land. And when you say, "Oh no, I wanted a retaining wall," I'm gonna say, "No, just look at it from this perspective."
I guess so, but a straight line in 3-dimensional space. So, like, you might be talking about a top-down perspective of that line. It's straight in a 3-dimensional space, you would say, but you wouldn't know how it's curved from a different perspective.
Yes, can end up with a line with an arc that appears straight if you look at it from a particular
Right, so a
direction.
sphere
But I would absolutely not say that straight lines are curved, because in that case the term straight loses any and all meaning. Right. But the path
Yeah.
the path of minimum distance between 2 points on the surface of a sphere is the arc of a great circle. And the distance along that arc can be calculated using the Haversine formula. We can apply that to Earth if we know the latitude and longitude of the 2 points involved. So if you give me the latitude and the longitude of any 2 points on Earth's surface, I can use a spherical formula to calculate the distance between them. And if you can prove to me that that distance is wrong for any 2 points, all I'm doing is giving you the formula. You can apply it to whatever pair of points you want, right? If you can prove to me that the Haversine formula is significantly inaccurate, and I say that because despite our friend's assertion, there are limits to the accuracy of each and every measurement and each and every observation and each and every construction. Nothing is perfectly accurate. And certainly the Haversine formula we know is based on spherical geometry, and the Earth is actually ellipsoidal, so it's going to have an offset there. But it's a good estimate. It's a good estimate for the distance between any 2 points on Earth's surface. All you need to do, all any flat earther needs to do to get people to stand up and take notice, is to find me 2 points for which it doesn't produce a good estimate.
Okay, so that's a burden of proof reversal fallacy and also an argument from ignorance. So
in what sense? In what sense is a falsifiable claim?
I'll tell you exactly what sense. The sense of that you are claiming that there's no evidence against my point, therefore my point is true.
No.
That is the definition.
No, that's not what I said.
Yes, well, okay. Bare minimum is
given that I have repeatedly produced evidence about the shape of the Earth that you have willfully ignored, and then you come in when I say, look at this over here. If you can prove that this is wrong, you'll be proving that the sphere Earth. This is your opportunity to prove your case.
Lack of evidence against your point does not make your point true.
No, the travel time of fucking seismic waves. The travel time of seismic waves does demonstrate a spheroidal Earth. And again, if you want to demonstrate that it doesn't, and the fact that the Haversine formula is always correct is evidence of the spheroidal Earth. And it's up to you to prove that it isn't evidence of a spheroidal Earth. This is not a reversal of the burden of proof. We use the Haversine formula all the fucking time, right?
Yes,
to calculate distances.
Tony has produced evidence. He hasn't claimed evidence. He's produced evidence.
And you guys have ignored the evidence and refused to provide any counter arguments, and now you're accusing me of logical fallacies for not producing any fucking evidence. Fuck you!
That's really strange to me. They're literally saying that you're basically lying, Tony. Come on. We all know you're lying. What the fuck? He's not lying.
It is the most idiotic. I've been here producing evidence, and people have been whining about me talking too much, and then they had the temerity and say, "Well, you didn't produce any evidence. You're just claiming it." Fuck off, then. If you're not interested in the evidence that I'm presenting, and I am presenting evidence,
so now you're still now? Okay.
No, I'm describing what you did.
He's produced evidence, but you
Via
guys
straw
are
man.
too stupid to realize the evidence that he's produced. So,
Well, I realize
don't
it's
know.
evidence. They're just too
Okay, we'll just rack them up.
It's not an evidence if it's true.
Because I said stupid, you're now like going against Tony. Come on, this is
Stupid is
against me.
You know, oh God. You know, it's unclear whether it's because you're stupid or because you're simply
Willfully,
you're.
I think willfully ignorant.
So now it's a false dichotomy? Okay.
No, it would only be a false dichotomy if both options were false. You need to prove, prove to me that the Earth is not a sphere. Any proof. Any fucking evidence whatsoever.
So you want me to prove a negative now?
You have to prove.
That's not.
That's
not proving a negative. What could be said about that is we're looking for evidence of a flat Earth. So present evidence of a flat Earth. That's all people are asking for. Like, please present more evidence of a flat Earth.
Or present evidence again that counters the evidence I showed you for gravity and the geometry of the Earth.
That's not
One
the
of the
same.
two.
That's not the same as providing evidence for a false or for a negative. That's not the same. Because it really feels like you're like latching onto things that people who talk. You're like latching onto these things. Oh, you can't prove a false. You can't prove a negative. Oh, we're going to latch onto that. But it's not.
The argument from ignorance fallacy can be applied to instance for God. You know, saying that God doesn't exist because there's no evidence that he does, or saying that God does exist because there's no evidence that he doesn't. Those are arguments from ignorance, right? But here we actually have data. I have shown you data. I've shown you observational data, multiple classes of observational data demonstrating the existence of gravitational forces, the accuracy of the Newtonian formulation of gravity, and the geometry of the Earth as inferred from seismic travel times. And this is information that you didn't have at the beginning of the conversation, and you've made no effort to engage with it. You've made no effort to refute it other than, well, somebody will be able to refute it at some stage, which is precisely an argument from ignorance. At some point in the future, somebody's going to come along and provide evidence that the seismic data is wrong. Well, until that happens, we're going to go under the assumption that it isn't, if that's okay with you. Right?
Yes,
and so
it's correct. Right? It's correct until it's proven wrong.
So how about, you pony up? Where's your evidence? Where's your data? And don't give me this shit about constructing a horizontal line. Talk to an engineer. The guys who get paid more than you do because they know more. Oh, can I take it from the silence that you don't have any evidence?
I can take it from the silence that I understand that you're bowing out of the conversation because you said to ask somebody else. You said to ask somebody else, so I will.
If you enjoyed the content, please support On the Level and future projects. Membership subscriptions available now, or come and get involved at Next Level Discord server. Thank you.